Good morning, everyone. There is only one announcement, and that would be don't forget your quiz. It's going to be due on today, 11:30 p.m. Eastern Time. And that's pretty much it. Okay, let's jump. Oh, another one. Today there will be a tutorial, and I will talk about condition variables. Just we'll see an example, an implementation of reader, writer, lock with condition variables and monitors. Okay, so let's recap what we saw or what we discussed in the previous lecture. So we were talking about take 3. In take 3, we have the class mutex, and it has 3 variables or 3 elements, a Spinlock, which we'll use to change the state of the mutex. It has a variable called value that indicates whether the mutex is locked or unlocked, and a queue, a waiting queue, which we'll use to put all the threads that are waiting for a locked mutex so that they don't busy wait. So we saw the implementation of lock, and we saw the implementation of unlock. It's very similar to what we did with interrupts. So now one question: can interrupt handler use this lock? The answer is no. We cannot let the interrupt handler use this lock. And the reason for that is that the interrupt handler is not a thread. So anyone who wants to use this lock, if they want to access a locked mutex, their state is going to change to waiting, and they're going to be put to waiting. And we don't want to do that with interrupt handler, because interrupt handler is not a thread. So we cannot put it into sleep. So we cannot suspend an interrupt handler. Therefore, this is not a lock to be used by interrupt handler. Another question: how should we protect a data that is shared by interrupt handler and a kernel thread? How can we do that if that's what we want to do? Let's say we have a shared data. How can we protect it from race conditions if kernel threads and interrupt handler want to access? So the answer to that is we can use spin locks, because as you saw with the spin locks, we're not suspending anything. So if something is waiting, they're busy waiting. Now, that brings another issue. So there is no problem. We can use the spin locks because they don't treat the code as threads. So that's one good thing about them. But we have to avoid deadlocks. If we use spin locks, there could be a condition that we might have a deadlock. For instance, let's say a thread locks a spin lock and then gets interrupted, and then the interrupt handler wants to access the lock or the mutex the spin lock, and well, the spin lock is locked, so the interrupt handler would busy wait, and there we have a deadlock because interrupt handler cannot terminate, and if interrupt handler doesn't terminate, then the thread cannot unlock the spin lock, so we have a deadlock. To avoid that, every time we lock a spin lock, we have to disable interrupts. We have to make sure that an interrupt cannot happen after we lock the spin lock. After you lock a spin lock, you have to disable interrupts. Sorry, before you lock a spin lock, you have to disable interrupts so that no interrupt happens, so that you don't get into trouble. So any spin lock that you, so this is the gist of it, any spin lock that is going to be shared by a thread and the interrupt handler, anytime you want to lock that spin lock, you have to, before doing that, you have to disable interrupts. Now, let me give you one example of such a spin lock that is shared between threads and the interrupt handler, or could be. Here's one. The spin lock for, oh, let's go. This one is one example with a scheduler. So if you remember, scheduler also has a spin lock for its state. So this spin lock that a scheduler uses could be also accessed by the interrupt handler, because interrupt handler, let's say it's a timer, could call the scheduler to schedule another task. Let's say the timer goes off and we decide to context switch between two threads. Now the interrupt handler might call the scheduler to schedule another thread. And when you call the scheduler, you're going to change the scheduler's, you probably will change the scheduler's state, and you want to acquire its lock. So you don't want that lock to be locked inside when you're in the interrupt handler. So here is then why we disable interrupts before we lock the scheduler spin lock, so that we make sure that no interrupts happens after this spin lock is locked. I hope that makes sense. So the reason for having this disable interrupts here is because we don't want the interrupt handler to be called while we're inside here that we have locked this spin lock, because then we might have deadlock. Okay. So the first thing we do here, we're implementing suspend. And if you remember, we pass the spin lock pointer to this suspend. And here scheduler unlocks it. This is the spin lock associated with the lock, the mutex, right? This is the spin lock of the mutex. So the thread locked the spin lock of the mutex and put itself to sleep by calling this suspend, and then pass the spin lock to this so that the scheduler can unlock the mutex's spin lock. Here, we just changed the running TCB's state to waiting. We add it to the ready list, and then we choose another one. We call thread switch. When we come back here, anytime we come back here, we just change the running thread state to running. So like always, this should now become something that you're familiar with. Every time you come back from thread switch, you come back to the thread that was context switched. So you change its state to running now. And then we unlock the spin lock, we enable interrupts, and that's it. This is make ready. So this was called when someone unlocks a mutex. When they unlock the mutex, they check if somebody is in the waiting list of that mutex, and if there are, then they choose one and then they make it ready here by calling the scheduler. Like before, you disable interrupts, you lock the scheduler's spin lock, you add that thread to ready list, make its state ready, you unlock, you enable interrupts, you exit. And that's pretty much it. So I explained this question, why do we disable interrupts, is because we want to avoid deadlock. What might happen if we unlock the mutex spin lock before suspend? So what happens if we do this one, this line, spin lock unlock, instead of inside the suspend? What if we do it before calling suspend? Then the same exact bad things could happen when we were discussing where we should enable interrupts. If you remember that the arrow was going up and down, where we should enable interrupts. And we decided that we shouldn't enable interrupts. We should let the next thread enable interrupts. Now that here we have a scheduler, we will let the scheduler unlock the mutex. So we cannot do it ourselves before putting ourselves to sleep. So we have to put ourselves to sleep and then ask the scheduler to unlock the mutex. Okay, I got 2 questions. Let me answer them. The first one was, sorry, what does the scheduler suspend do on high level? Does it stop a thread from running? Yes. So the suspend basically just suspends a running thread and unlocks the mutex as a Spinlock. Just wondering, where is the mutex Spinlock defined? Sorry, I just continued from the last lecture's slide. So if you're interested, it's defined here. Here in the mutex. Here in the mutex, we have a Spinlock for the mutex. So we're going to use this mutex every time we want to change this value, or every time we want to change the status of this waiting queue. The same here, the scheduler also has a Spinlock that we will use every time we want to change the state of the scheduler, which is basically changing this ready list. Okay, so that just to recap what we talked so far, and to just compare the 2 methods, basically take 2.5 and take 3. Here I put them side by side. The lock that we implemented using disabling interrupts and the lock that we implemented using the Spinlock. Sorry, the mutex. I keep saying lock. The mutex we implemented using enabling and disabling interrupts, and the mutex lock that we implemented using Spinlock. As you can see, the body is almost the same, almost. Here we disabled interrupts, and at the end we enabled interrupts. With Spinlock, we locked the Spinlock, and here inside else we unlocked the Spinlock. The reason that we're doing it here inside the else and here outside the else is because of the use of the scheduler, right? Because now with the scheduler, we're unlocking the Spinlock inside the scheduler. If you remember, with disable interrupts, we had this invariant which said every time you wake up, you should enable interrupts, right? But here with the Spinlock, we can just do it in the scheduler. So we just we don't need to do it when we wake up because the scheduler has done it for us. Okay, so we just basically very high level, instead of disabling interrupts, we call Spinlock.lock, and instead of enabling interrupts, we do a Spinlock unlock. Now, just to recap, what did we want to do? Well, we had a kernel that has multiple threads. Now we want to provide support for critical sections and race conditions. So we have to implement mutex and also other stuff, which we will talk about, but for now, mutex. So we want to be able to work in critical section by just calling mutex lock and mutex unlock. So that was the problem statement. Now, how do we implement these two? We saw doing it very naively with disabling interrupts and enabling interrupts. The problem with this was that depending on how big this critical section is, you could be disabling interrupts for a long period of time. And that's not a good thing because during that time, even the operating system cannot take the control back. So this is bad. the other bad thing about it was that user level code cannot use it. User level libraries cannot implement it because enabling and disabling interrupts are privileged instructions. And it also works on uniprocessor. It doesn't work on multiprocessors. So we made it better, a little bit better. We dealt with the busy, the other, yeah. So we dealt with that, with some of those problems with this other implementation, right, where we introduced a value and used disabling interrupts and enabling interrupts to just change that value. So now the duration at which the interrupts are disabled are only that duration only depends on these lines of code. It doesn't depend on how big this critical section is. So we eliminated the dependency to this critical section, and this is better because hopefully this few lines of code are fast to be executed. The same with disabling interrupts. Then we said, okay, how do we how do we support multiprocessors? That's where we introduced the Spinlocks. We implemented the Spinlocks with test and set. So again, a naive implementation was to just do lock while test and set value and then unlock value free. The problem with this was we had busy waiting because any thread that calls this lock, if the mutex is already locked, then they're going to just stay in this while loop, and this is busy waiting. So instead, we improved this implementation by this other implementation where we added a value and a queue. So every time the mutex is locked, we can put the waiting thread in the waiting queue. Okay, so so this was very high level. If I were to give you an example of how Mutex is implemented in Linux, it's a little bit there is more optimizations obviously done. We don't stop there. We can optimize this even more. So there are two things that would enable some more optimization. The first thing is an observation that mutexes are usually free. So this is the first observation people have made. You could have a condition where the mutex is very much busy, but in most of the cases, 99% of the cases, mutexes are usually free when you acquire them, and race conditions are rare. So this is one observation. The second observation to make is that hardware provides other atomic operations as well that we can use. It's not just test and set. You can do other kind of like atomic instructions like atomic increment and atomic decrement or atomic exchange. So the Linux implementation uses these two observations and facts. So it has a fast path and a slow path. So with the fast path, it just very quickly checks if the mutex is unlocked by using an atomic increment or decrement to just check if the mutex is free or not. If it is free, then in 2 instructions, it locks the mutex. So this is the fast path, which usually will be the case. Usually the mutex is free. So with 2-3 instructions, Linux locks the mutex and lets the thread go. And if, however, the lock is unlocked, the mutex is locked, so if we are unlucky, then we just go the slow path, which is basically what we just talked about so far. So we take the same implementation that we just saw in the previous slides. So here is like just high level code. There's a struct of mutex, let's say. There's a count we tell the hardware that this is an atomic count. So we want to do atomic instructions on this count. This is the way we're telling the hardware that we're going to do this. We still have a Spinlock. We still have a queue, right? So this is the fast path with lock. When we want to lock, we can just decrement. This DECL is an atomic decrement. So it atomically decrements the value of the lock. And if the value is now 0, it means that if the value was 1, meaning that if the lock was free, so we just locked it. So here we jump to critical section. So we jump to 1, and this will be our critical section. So basically in 2 instructions, we just locked. This was our fast path. Now, let's say that the lock was not 1. Let's say it was 0. Now the value of lock is not 0. So we just here call the slow path, which basically goes to the implementation that we saw previously, the ones that I showed you, something like that. So then we take the slow path. Yeah. So here, what you need to do is that there is an instruction. This is an atomic decrement, and we're telling the hardware that we're going to do atomic operations on this count by this. I got a question. What did you mean by mutexes being free, as in they don't require additional hardware to implement? No. So what I meant by usually mutexes are free means that usually mutexes are not locked. So they're usually unlocked. Let's say you implemented a multi-threaded application and you have critical section and you want to lock and unlock your mutex. Usually, not always, usually the mutex that is going to be called, the lock that we call on a mutex, usually the mutex is unlocked and you can easily lock it and do the critical section and get out. And the next thread that comes sees the same thing. It's very unlikely or rare, or it happens not frequently, that somebody else has acquired the lock and you have to wait. It could still happen. That's why we have the slow path. So we say in cases where the mutex is unlocked, let's in 2 instructions lock it and get over and do our job instead of spending time on it. And if it is locked, then we take the slow path. And hopefully this helps. If, however, you have a mutex that is like 99% of the time locked, then these instructions add a little bit of overhead, because you always are going to, take this a slow path and you're just adding 2 or 3 more instructions. So you have to make a decision which implementation you want to choose. Usually you have different implementations that you can choose from. Okay, are we going to implement Mutex in lab 3? You're lucky, no. I wanted you to, but because the board that we have is a multi-core board, so it has multiple cores. So we actually wanted to use both of cores, that it has 2 cores, and we wanted to ask students to implement Spinlocks and Semaphores, but unfortunately already the lab is too much, so adding that would have made it even harder. So we decided not to take that path. So you're fine with the lab, but I still think that many find this interesting to know how it's implemented, because you probably so far have just used it without paying much attention on what goes in implementing Semaphores, Mutexes, monitors, and such. So that's that. Okay, warrants we overlocks. So here, some last discussions on locks. The implementation that I've talked to you so far, it was kind of like just function calls, right? We had this class of mutex, and then we were just calling lock and unlock. Now, if you want the user space threads to use your kernel locks and data structures, you have to use the interface, the system call interface. So what we've seen so far would work with between kernel threads inside kernel, like just function calls and stuff. The moment you want to make it available to the user space threads, then you have to go through the system call interface, and that provides some corner cases, because when you call system call, you disable interrupts. So there is some stuff that you have to take care of if you want to use this implementation and provide system call interface then for the user space programs to use your locks. An alternative to that is to just implement locks in user level library. So the same way that I talked about how user level libraries can provide multi-threading, right? They can create threads inside their space. That's up to them. They can also create locks and implement locks and provide locks inside user space so that you don't need to come to the kernel. And that's possible using this test and set because it's not a privileged instruction. So now we have an implementation that we can give it to, we can implement it in user space and be fine with it. Okay. Oh, questions. Just to confirm, fast path is nothing is locked. So the first thread would go through, but if more threads come, it would slow down since it would start locking. Sort of, yeah. So with the first 2-3 instructions, if you're the first thread, you will go through them. Hopefully, you will release the lock before another thread wants to acquire the lock, so that the next thread that wants to acquire the lock also goes through the fast path. But in an unfortunate scenario where you lock it, you're the first one, and then another thread comes while you have locked the mutex, they would go through the fast path and then they would branch to the slow path. So there is some overhead because then they have to also execute those 2-3 extra instructions and then realize that, oh, the mutex is locked and we have to go through the slow path. Whereas if you didn't have those, everybody would go through the slow path. So there's a trade-off there to be considered. Okay. So never access shared data without locking a mutex, without providing support for your critical section, right? So these are things that you probably have dealt with in 252. I'm just bringing it up again. When you have a mutex, it has to be initiated free. You have to always lock the mutex before accessing your shared data, always. And the best practice is to do it at the beginning of your function. So if you have a function that at some point accesses shared data, it's always a good practice to lock the mutex at the beginning of the function. Don't think that, oh, it's like high overhead. I just use the lock at the beginning and end of my critical section. If that's the case, then just take that piece out, make it a function, so that at the beginning of the function you can lock the mutex, and at the end of the function you can unlock your mutex. So these are good practices that make your code readable. And then whoever locks the mutex should unlock it as well. Don't throw it to someone else. Okay, so this is an example about lock the mutex before accessing shared data. So let me actually talk about it. So let's say that you have a single tone structure. So you want so there is an object that you want to create once, and once it's created, everybody should just use it. You don't want to create it again. So the first time that the pointer to that object is null, you want to create the object and then set the pointer, and then from there on, you just want to use that object. You don't want to create new objects. So let's say that there is the function getP that returns the pointer to that object. And this is an implementation. It says, okay, I first check P. If P is null, then I want to create it. So how do I create it? Okay, I lock the mutex. I check it again. You will see why we need to check it again. But I check it again. If it's still null, then I allocate space, I set the fields, and then I set the pointer. So P becomes this temp where we allocated here. And then I unlock the mutex, I return P. So does this work? Now, if you think and start scratching your head around this and spend some time, you will realize that it's actually not gonna work. The reason is basically what you see in the title. Lock before accessing shared data. This P is shared data. Even when you want to read it, here you're reading it, if P equals null, you have to have the lock. If this mutex should be moved at the top, you should check if P equals null by having the mutex. Now, you might ask why people would move it here inside the null. This is an optimization that some people thought that would make sense, because this code here, we're going to do this code only once. We're going to create this object only once. So it's kind of pain to lock the mutex every time you want to get the pointer, when this code is only going to be executed once. So some people thought that, okay, we will just put the mutex at the beginning and end of this code, and we hope that this is going to be only executed once. So every time after the object is created, I'm not going to write anything. So I can just read this and return P. Now, this unfortunately won't work in modern processors, most of the processors that we have. And the reason for that is your processor usually is out of order processor. Also, compilers sometimes reorder instructions. Hopefully you've seen these in 252 or other architecture courses. So one thing that could happen is here, this instruction P equals temp only depends on this temp equals malloc. So when P is gets its value from malloc, this instruction could be executed. This instruction does not depend on these two instructions. These two instructions set temp. So compiler could, or the hardware could, execute this instruction out of order, right? And then execute these two. As a result, you could set P to temp before setting the fields for this P. Now, let's say the first thread comes in, sees that this is null, locks the mutex, and allocates space for temp, and then this instruction executes before these two. And let's say at this point, timer interrupts goes off, you context switch to another thread. Another thread comes in. What do? They just check this if P is null, and well, P is not null because you have already executed this line. You still haven't executed these two lines, so temp is just a pointer that the structure is not actually set. So here they would return P, and they would use that P which is not initialized correctly and this would not work. So how do we check this? Fix this. We do this with double check locking. So this is how we do it in a safe way. Every time you want to access your shared data, call mutex and then unlock the mutex. So although this has high overhead, because every time you want to get P, you're going to lock the mutex and it might not be necessary, but it's the safe way to implement this. So this is just one example to show you something that looks pretty innocent and feels like it would execute correctly. It might not. So always lock your mutex before you access your data structure, your shared data structures. Okay, next stop is semaphores. Give me a sec. Okay, we saw how to implement mutex. Let's now switch gears and talk about semaphores. How do we implement semaphores? First of all, let's just recap what semaphores are. So they were defined by Dijkstra in late 60s. This is a Dijkstra font. I think it is free, I believe. And it's based on his handwriting. It's very cool. So he introduced it in late 60s. And this is actually the main synchronization primitive used in original Unix. And it's very much used in Linux kernel as well, as far as I know. Semaphores have two non-negative integer values, and they have only one non-negative integer value and two operations, P and V. So hopefully you've coded a lot with semaphores, so you should probably know this. So P waits for the semaphore to become positive, and then it decrements, and V basically just increments the semaphore by 1. And after incrementing it, it wakes up a waiting P. So that's pretty much it. I have a cool animation. I'm not going to spend time. You probably know it. I spent so much time on that animation. It's waste. It's such a waste. I did it for SE 350 because SE students didn't know semaphores, did not have not or yeah, when they take operating systems, they have no idea, most of them, semaphores. So this was a cool animation for them, but you guys know, so I'm gonna just skip. So now let's implement semaphores. This is the P function implementation. Excuse me. So I'm not showing the internals, but as you can see, the semaphore has also a spinlock, a value, and a waiting queue. Very similar to locks. So at the beginning of the P function, I lock the semaphore, I check the value. If the value is 0, so this is the P function. So if the value is 0, then I add the thread to the waiting list, and I call the scheduler to suspend the thread, and I just pass the semaphore spinlock for the scheduler to unlock this. And else I decrement the value. So this P function decrements if it is positive, right? If the value is 1, then it decrements it, and if the value is 0, then it just puts it into sleep. It doesn't decrement. Okay, so one thing that was kind of confusing for students last term, let me mention it. Here we say P is an atomic operation that waits for semaphore to become positive, then decrements it by 1. So P always decrements, and V always increments. So this is the syntax or logic of P and V. Now, in the next slide, we have implementation. So the implementation should resemble the logic, should do or follow the logic. But as you can see, in this implementation, if the value is 0, then the value is not going to be decremented here, as you can see. So if I come to this if, I'm going to be just suspended here. And I'm not going to decrement the value. And if the value is not 0, then I will decrement. So some students had some difficulty why we're not decrementing all the time. Well, the reason is very similar to the mutex stuff, that if the mutex was locked and you suspended yourself, after you wake up, it means that somebody else kind of like unlocked it and now you're going to lock it again. So we don't make somebody else to unlock so that when you wake up, you don't need to lock it. So that's what's going to happen. So in V, as you will see, if somebody is waiting, we're not going to increment so that whoever is going to wake up here doesn't need to decrement. But again, in the logic of P and V, we have this incrementation and decrementation. In our implementation, however, we do some optimization, right? We don't want to do things twice. We could potentially, I'm not saying that this is a good implementation, which is not. It could cause other problems if you increment. But that's what we're doing. So the logic of PMV has this increment and decrement. Our implementation, however, does some optimization. So somebody's asking, is Semaphore Spinlock the same as Mutex Spinlock, just renamed? These are just, yeah, yes, we are just using the Spinlock class or structure that we introduced before. So we introduced the Spinlock class or structure, and now we're just using it, right? Now, here is the Semaphore V. Again, locking the Spinlock, unlocking it at the end, and yeah, so here, as you can see, if somebody is waiting, we're not gonna increment. If nobody is waiting, we'll increment. So hopefully this makes sense, because if somebody is waiting, we're logically incrementing it here and then waking them up here, and then they would decrement. So we basically cross over this decrementation with this incrementation here with these two, right? So we don't increment here so that we don't need to decrement here. However, if the lock is, if the mutex is this, if the semaphore is positive, we just decrement. If the semaphore is, if nobody is waiting, we just increment. Now, question again, can interrupt handler use this semaphore? It cannot use the P function because here we suspend, very similar to mutex, but it could potentially use the V function, right? Because here we're not suspending anything. So potentially you can call V, but you again have to make sure that if you want to use this, if you want to have a semaphore that is used by the interrupt handler, you need to disable interrupts and enable disable interrupts here at the beginning and disable interrupts at the end. So in this implementation, you cannot use it with interrupt handler. If you want to have it though, you could potentially add disable interrupts and enable interrupts at the end, at the beginning and the end, and then it would be safe for the interrupt handler. We would avoid deadlock. So yeah, I got a question. I'm sorry, but can you explain once more why we don't increment anywhere? No, we are actually incrementing somewhere. Here we're incrementing. So we increment if nobody is waiting. So if nobody is waiting, we increment. But if somebody is waiting, logically, we first of all put them to ready, and then we don't increment because they don't decrement. They just assume that value is 0. So what would happen is kind of like, okay, I'm going to make the value 1, and then you're going to wake up and then make the value 0 again. But then what's the point? The value can remain 0 as long as this guy wakes up, the one who is waiting, and then gets out without increasing or decreasing the value, right? So if, however, nobody's waiting, then I can just increment. Just look at the code, it will make sense. Okay. Now, although I know, give me a sec. So in 252, as far as I know, you probably used Semaphores a lot. You implemented projects with it and stuff. But they are not, they are harmful, as your textbook puts it. And this is from Dijkstra's article. So he himself pointed out that that Semaphores ended up being used in 2 completely different ways. So basically, they are so powerful that you can use them in 2 different contexts. You can use them to create mutual exclusion, as you probably have seen. So you could have a binary semaphore and use it as lock and unlock. You can also use semaphores as primitives for scheduling. What do I mean? Let's say you have some constraints on, how many people should wait, how many events should happen for someone to wake up and stuff. You probably have done that as well in 252. So let's say I want to do something after something happens, right? It's kind of like a scheduling thing. I want to say I don't want to change this value if nobody has changed it before me. So I call on P to wait, and then somebody else does it, and then I wake up. Or I want to see 3 times this value is changed before I change it. So all of these things, you can do them with Semaphore as well. So we ended up doing both of these. Scheduling, that's what we call them, like adding constraints to your program, and also mutual exclusion. So these are 2 things that we're using Semaphores for. And that makes Semaphores harmful because they make your code unreadable and hard to follow. I bet you have had those situations. Somebody puts a code in front of you with semaphores, and you have to scratch your head to figure out what the code is doing. Is this semaphore used for constraints? Is this used for mutual exclusion? It's just complicated because it serves 2 purposes. And we don't like that in modular programming. We want everything to have a single functionality and then be used for that single functionality. As a result, what your textbook suggests, and what I actually agree, is let's put semaphores aside and not use them at all. They're harmful. We actually can use monitors instead of semaphores and get the exact same thing with a lot more clear coding. So what is a monitor? A monitor is a bundle of a single mutex and 1 or more condition variables. So we're going to use the mutex for mutual exclusion, and then the condition variables for scheduling or for putting constraints on in our programs. So we're basically getting the same functionality that we were getting out of semaphores with monitors. Now it's much cleaner. Every time you actually want to have mutual exclusion, use the mutex. And every time you want to use constraints, use the condition variables. So that's what we're going to do. So now, what are condition variables? You probably have seen them, but not worked with them. That's why we have the tutorial today. So in the tutorial, I'll walk you through the code of readers and writers lock, which I'm pretty sure you saw in 252, its implementation with semaphores. Now we will see its implementation with monitors. It's much cleaner, much more understandable, you will realize. So just to recap what the condition variables are. So condition variables are primitives that provide three functionalities. One is wait, one is signal, and one is broadcast. So any condition variable has to be associated with a lock. That's why any monitor needs one mutex. So each monitor has one and only one mutex and one or more condition variables. Now, any condition variables in a monitor, they all use the same mutex. Now, what is this wait function? This wait function is used every time you want to put a thread to sleep, waiting for an event that you are going to come up with in your program. These are what I called as scheduling things or constraints. Whenever you want to, define some events that threads have to wait for, we'll see an example of this. So the syntax of it is that you wait and you pass a mutex to this wait. And what this wait is going to do is that it's going to put you to sleep while you're waiting for that event, and it's going to release this mutex. So you're going to use this mutex to protect any critical section that you have in your code. And then inside that critical section, you're probably wanting to wait for an event to happen. And then if that event hasn't happened, you call wait on that event. But then before you're suspended, you have to release this mutex to allow other threads to make that event happen so that you can wake up and do some stuff. And then you have signal. This is a function that we use to signal one thread from those threads that are waiting for an event. And then we have also broadcast, which wakes up everyone who is waiting. Okay. Now, properties of condition variables. Condition variables are memoryless. What does that mean? It means that they have no internal memory. They don't memorize how many times signal and broadcast have been executed or even wait. So they don't memorize that. I think with wait they do memorize, but then with signal and broadcast they don't memorize. What do I mean by that? So what I mean by that is if you don't have anybody waiting, if nobody has called wait, and a thread executes signal or broadcast, they get wasted. Your system doesn't memorize this. Now compare that with the v function. So with the v function, even if you haven't called p, your v function is going to increment your semaphore, the value of your semaphore. So it's basically you're memorizing it. So next thread that calls p could go through if somebody else before called p. But with condition variables, even if you call a million times, call signal a million times and nobody is waiting, and then somebody comes and calls wait, they're going to wait. They're not going to say, oh, the signal was called a million times so I can go. No, none of those signals are memorized. So all of them are wasted because nobody was waiting. So this is one important and significant difference between condition variables and semaphores. I will answer the question I got once I'm done with this slide. So another thing with condition variables is that they depend on the mutex. They're not independent entities. They have to have a mutex associated with them. They have to be defined in the context of a monitor. And this means that you are allowed to call wait, signal, and broadcast only in your critical section, which is protected by the mutex. So every time you want to call signal, broadcast, or wait, before that you must call mutex.lock. So you should be inside critical section to call these functions. Some people tell you differently. Some people say it's safe to call signal or broadcast without locking the mutex, but just ignore them. And always, always, always call these functions inside your critical section while the mutex is locked. And calling wait atomically adds a thread to wait queue and unlocks the mutex, as we will see the implementation. A thread that is re-enabled by signal or broadcast does not run immediately in some implementation. I guess I have to add this. I guess I will leave it as is because the other implementation, there are two implementations of condition variables. One of them is just in theory. There are no known implementations of it. So in all the implementations that are available that I know, after a signal, once a thread wakes up, once a thread gets a signal or a broadcast message, it doesn't mean that they're going to run immediately. It just means that their state is going to be changed to ready. Their state is going to change from waiting to ready. And they will be scheduled at some time. So bear that in mind. Okay, let me answer the questions I got. Does P represent how many threads are waiting, and V represents how many threads are currently running? It's hard to say, really. It depends on how it's defined. What kind of, again, in the context of mutexes, not really. If you have a binary semaphore, that's not how it works. If you're in some other cases, it might be. So it's really, that's one of the things that it's just hard to reason about P and V in the context of mutex, in the context of semaphores. So is that we use it only for good coding practice? That's not, you shouldn't be this dismissive. Like, is that just this? Because good coding practices are very important. When you're writing a code, you want your code to be reusable, you want your code to be maintainable, you want your code to be understandable by others. So it's not just that, it's actually a big thing. In a sense, yes, because semaphores are working and they're actually being used in many applications. So we don't have anything against their functionality. They work, but it's just hard to follow them. It's hard to reason about a code that uses semaphores, as you might have seen it in the past. Whereas when you use condition variables and monitors, your code all of a sudden becomes very, very readable. Huge difference, as you will see in some examples that I show. Okay, now I'm going to walk you through an example of using condition variables and monitors to implement a bounded buffer. So I will talk about the implementations of condition variables, but this is just to refresh your memory with condition variables. Here is my monitor. So my monitor has a mutex that I'm calling mutex, and it has two condition variables, empty CV and full CV. So this is my monitor, has one condition variable and one mutex and two condition variables. Now, in my bounded buffer, I'm going to have producers and consumers. So producer is going to produce an item, and consumer is going to consume an item. I want the producer to wait if the buffer is full, and I want the consumer to wait if the buffer is empty. Then I want the producer to signal any waiting consumer if a new item is put on the buffer, and I want a consumer to signal a producer once they pick up an item or they consume an item from the buffer. So what I just said were constraints or scheduling constraints for my bounded buffer. So for the scheduling constraints or for the constraints that I talked about, I want to use my condition variables. And every time I want to change the state of my bounded buffer, I'm going to just use the mutex to protect it. So the mutex will be used to protect the critical section, which is every time I want to check the state of my bounded buffer. And the condition variables I'm going to use every time I want to create constraints for scheduling different threads. Okay, so at the beginning of my produce function, I'm going to lock my mutex. As I just mentioned, this is the practice you should do. Then I will check the size of my queue. If the size of my queue is full, it's a bounded buffer. So if it is full, I'm a producer, I want to put an item. But if there is no space, then I'm going to call the full CV condition variable and wait on it. So full CV is a condition variable. I'm going to call wait on this, and I'm going to pass the mutex. I lock the mutex. I'm going to go to sleep here. So I have to pass the mutex to this wait function. Hopefully that makes sense. Now you might say, why do you have while here? I will explain. So this while, I will explain why it's while and not just if. Now let's say at some point I get out of this while. Let's say that there is an empty space. Then I just put my item to this queue. I add it. Once I add, I signal consumers. So consumers are going to be waiting on this condition variable, the empty CV. So I signal them. I say, I have actually put an item. So if somebody is waiting, if the queue was empty and somebody was waiting for it, wake up and go and consume that item. And then I unlock the mutex and I'm done with produce. Now let's look at the consume function. Again, I lock the mutex. This time I check if the queue is empty. And if the queue is empty, I will wait on this condition variable. Let's say I get out of it by a signal, or let's say at the beginning it wasn't empty. Then I remove. The moment I remove, I want to signal the producers. So if any producer is waiting, I will signal them. I will say I have consumed one item, so there is one space for you to put your item if anybody is waiting. And I unlock the mutex, I return the item. Now that's it. That's the code. Here, once the produce signals an empty CV, now here, listen to me this one carefully. we're getting some details of the implementation of condition variables. So what's going to happen? When the signal is received here, the thread that was waiting, that called wait, so this signal will pick one thread with some algorithm that we don't care. So somehow, randomly, it's not usually random, it has some logic, but we don't exactly know how. It's not first come, first serve. So one thread, let's say multiple consumers are waiting. So let's say the queue was empty. So we call this consume 10 times. And now 10 threads that called consume are waiting here. So they're put to sleep and they're waiting. Now, let's say a producer comes, produces an item, and then signals. So this signal will wake up one of the consumers. What does that mean? It means that that consumer, that particular one that got the signal, the state of that thread will change to ready. It does not mean that that thread is going to run immediately. It could, but it doesn't. It's not guaranteed. It just changes its state to ready, and that's it. And then the producer finishes. Let's say at some point, the scheduler picks the consumer thread that just woke up. This thread wakes up. Where does it wake up? This is very important. It will wake up inside this wait function. This wait function at some point suspended this thread. This thread wakes up inside the wait function. What is the first thing that this thread has to do inside wait? The first thing it has to do, this is very important, is to acquire the lock again. Why? Because this thread, before being put to sleep, released the mutex. So the mutex, it just unlocked the mutex to go to sleep. Now it has waken up. It's inside its critical section. So before it can do anything, it has to acquire the lock. Now, the lock could be free or could not be free. One example. So the producer wakes up a consumer. Now the consumer becomes ready. The producer exits. Before the scheduler picks this right now waken up and ready thread, let's say another thread calls consume or another thread calls produce. And for some reason, scheduler picks that thread, that new thread that is going to produce or consume. And that thread could call mutex lock here or here. So they could acquire the lock. And then they could come and see, they could consume that item. Let's say it's a producer. So it doesn't want to consume. So it's a producer. It wants to put another item. And let's say at some point, it gets, the timer goes off and we come back to the scheduler and scheduler this time picks the waken up consumer. Now the consumer wakes up in the wait. It wants to acquire the lock. Well, the lock is acquired by the producer. So it goes again to sleep. Now, where does it go to sleep this time? It goes to sleep for this mutex. It's a different sleep. The first sleep, it went to the waiting queue of this empty CV. This second one that I just described, it goes to the waiting queue of this mutex because it wanted to acquire the mutex. The mutex was locked. So it has to wait for that mutex to get free. And then at some point, let's say it wakes up again and it can acquire the mutex. At that point, it gets out of this wait function. So we're done with the wait. We have the lock. Now, this is why I said you have to have it in a while. Why do you have to have it in a while? Because so many other things could have happened ever since you woke up. Because you woke up because some producer produced an item. But ever since, there might have been other consumers, new consumers that have consumed that item that you were woken up for. So now you have to check it again because you didn't run immediately after you waken up. You woke up. So this is why you have to have it in a while. And let's say, for the sake of argument, let's say the queue is not empty, so you can get to remove the item. So now let's, this actually brings us to this very important distinction between Mesa and Hor monitors. Poor guy, his name is Hor. Can a context switch happen inside the critical section? Yes, context switch could happen inside critical section. There's no problem with context switching happening in the critical section. If it happens, it would be safe because whoever wakes up, they would want to, they either have the, so if you context switch inside your critical section, you're going to context switch to someone else, which hopefully is not in the critical section. If you context switch to someone else who is also in the critical section, that's a bad thing, right? That's why we don't allow this dude who wakes up inside wait to get out of wait until it acquires the mutex. So you want everybody who is inside their critical section to have the lock. And if that's the case, then it's fine to context switch, even inside your critical section. So context switching doesn't mean any, context switching, it means just you go to some other ready thread. It has to be that if the critical section is protected by locks, you're sure that no matter how many times you context switch or to whom you context switch, that other thread is not going to be inside the critical section. That was a good question. So if the lock is in use, would the wait be in line for the lock right after it unlocks? No, because lock has its own wait queue, the mutex, sorry. So this mutex, so this MTCV has its own wait list, which here you put threads into. This mutex also has its own wait queue. So here, when you call mutex.lock, if the mutex is already locked, you're put to that waiting queue for this mutex. And here, when you wake up inside your wait, you want to acquire mutex again, you want to lock it, so you will be put in the waiting list. Now, there might be other people, other threads in that queue for this mutex. So there is no guarantee that you'll be the first one who will wake up, who will be picked after the mutex is unlocked. So there is no guarantee. That was a good question. Okay, so I'm gonna just point out to the gist of this. I'm not gonna spend that much time. So the Mesa is what I just described. When you get a signal, you're not gonna run immediately. Your state will just change to ready. That's it. With Hor implementation, after somebody calls signal, we're actually going to context switch to the signaled thread. So we'll run the signaled thread immediately after a signal. So this is the difference. Now, Hor will lead to cleaner code because with Hor implementation, you just need to use if, because you're pretty sure once you get a signal, you're going to execute. Whereas in Mesa, you have to use while. And that's not just this example. It makes it easier to reason when you're talking about, analyzing your code, because you just say, oh, signal, then this guy is going to run. However, implementing it, now that we're sitting in the kernel coder, you will soon realize that implementing Hor implementation, coding it, is much harder to make sure that whoever gets a signal runs immediately and all of that. It's going to bring a lot of headache. Whereas with Mesa, you just change the state and let it to the scheduler to decide who runs next. So implementation-wise, Mesa is easier. Analyzing the code-wise, Hor is easier. So here's example with Hor implementation. So here at the moment you call signal, you're gonna give the mutex and the CPU to the waiting thread. So you're going to context switch immediately and give the mutex to this guy so that this guy can run. Once this guy is done, you go back to the signaler and finish. Whereas in Mesa, at this point, all you're going to do after the signal is to just change the state of waiting thread to ready. That's all you're going to do, and put that thread to ready queue. And then you continue, you finish, and at some point, the scheduler will schedule the thread that was put to ready, and then it will be executed. And that's pretty much why you need while instead of if. Now, just to show you an example, let's just, for the sake of argument, instead of using while, let's use if with Mesa implementation. Let's assume that we have Mesa implementation, and instead of while, I use if. I actually looked at the ECE 252 instruction manual or the lecture notes. I saw that with condition variables, your instructor used if. So, but I didn't see any mention of Mesa or Hor. So this is important actually. When you compare to your lecture notes from ECE 252, because there seems to be that it was assumed that the implementation is Hor implementation, because I saw that the checking is happening with if. So if that's the case, that it implies that you're assuming that you have a Hor implementation of your condition variables. But in reality, Hor implementation doesn't exist. I haven't seen it. So it's all the libraries that I know use, like pthreads, Java, all of them have Mesa implementation. They don't have Hor implementation. So let's see what happens if we, instead of having, gosh, well, I have 2 minutes. Instead of having while, let's use if, see what happens. So here is the can I finish this in 2 minutes? I probably cannot. Okay, so I probably, I really wanted to finish this. I guess it's fine. So we probably will finish this in the next lecture. And I think I've given you enough information to run the tutorial today. So in the tutorial, we'll see another example, something like this one, the bounded buffer. So we'll see an implementation of readers and writers lock with monitors. Okay, so I think that's pretty much it. So thank you so much for. Oh, I got questions. Why do most operating systems use Mesa? As I described, implementing Hor is hard. Making sure that when you signal, you immediately run the signaled thread is hard. So nobody wants to deal with that implementation and making sure that the implementation is correct. Whereas Mesa is pretty easy to be implemented. Does Mesa Hor apply to all unblocking? Example for Semaphores. In an ECE 252 lab, we use Semaphore with if instead of while and had no problems. Yes, so the Mesa and Hor implementation only concern condition variables. They don't concern semaphores. We saw the implementation of semaphores. So with semaphores, you don't have any Mesa or implementation stuff going on. It's just with the condition variables. So with semaphores, you're fine with using if. It's just the condition variables that you have to be careful if or while. So Mesa and or is important. So in any quiz that you see, unless explicitly indicated, you should assume that the implementation is Mesa. Unless the question explicitly says that it's a HOR implementation. So other than that, from now on, we'll just assume that we have Mesa implementation. Thank you for coming to the lectures, and thank you for anybody who watches the lectures. Take care, be safe, talk to you in a few hours during the tutorial. Bye-bye.